today we'll go through back to the basics, basically going over kind of some of the basic concepts from a polyrheological standpoint in this case. And so the goal is to kind of give an understanding of basic theory behind what rheology is and how it can be explained and used from a polymer analysis standpoint, as well as recognizing various types of tests and techniques that can be employed in polymer applications, as well as kind of looking, and hopefully from this is you'll be able to understand and select kind of the appropriate measurements for the characterization of your materials going forward in this case. So kind of to get started, so what is polymer? So by definition, it's any natural synthetic or compound, usually of high molecular weight, of repeated lengths in this case, that create kind of plastics in terms of synthetic polymers in which we have a reaction that creates these plastics, or even from a natural standpoint, so even proteins, carbohydrates, biopolymers, hydrogels, all examples of kind of a polymer in terms of, so it's a wide description of kind of where a polymer kind of gets sorted out in this case. And so it actually can be put into different types of categories. So you have what are thermoplastics. So these are kind of materials that have long chains, either high molecular weight, low molecular weight. They may be partially crystalline or amorphous. They have a glass transition temperature at very cold temperatures where they behave like a solid. As you heat them up, they begin to relax and actually begin to flow or melt. So it transitions from a solid to a liquid. So examples of that are kind of polyethylenes, polypropylene, polycarbonate, et cetera in this case. Now, as you kind of create kind of cross-linking or network chains where the sample can no longer kind of flow, you create kind of elastomers or thermosetted polymers, in which the fact is they now no longer can fully relax. They behave like a solid throughout the whole temperature range. They do soften, but they're not possible from a recycling standpoint because, again, you can't melt it, you can't break it down without doing things of that. So things like elastomers, you can think of vulcanized rubbers, and then thermosetting polymers that kind of condition from, say, a fluid to basically, as you heat it up, you create this thermal set, which is something like an epoxy resin or polyester resins, where it fully cures and has a high degree of cross-linking in this case. And so what is rheology in a nutshell? So rheology is kind of the nutshell of the study of deformation of flow behavior, as well as deformation kinetics of all materials, from fluids to solids. So it comes from the Greek word rheo, meaning to flow, and ology, the study of in this case. And so in the field of rheology, you have a lot of different things. So you have dynamic mechanical analysis, you have viscometry, rheology kind of conditions all that. And so from the Greek word kind of pantareia, is everything is usually in some sort of state of flux or is flowing in this case. So as I said, rheology covers this vast range of materials. But with rheometry, which is various different types of techniques or systems, these are experimental measurements. So you can use a rheometer, a viscometer, a capillary design setup. In essence, we just kind of poke and prod at the material to kind of see its response back and get us a rheological understanding of the material under either different stresses, strains, temperature, or even pressures in this case. And so when we talk about things in terms of a rheological standpoint, we can look at flow properties and deformation properties. So when we look at flow, this is either applying a rotational stress or shear rate. So it's used to characterize fluids in this case. And when we apply a certain force to the sample, it begins to flow. So you can think of water or an oil or a fluid is you turn the container over, it starts to naturally flow out. So it does flow or move in this case. Now, in the terms of fluids, though, they have no memory. So as soon as I remove that force, so I flow from one container to another, it dissipates that energy, either in terms of flow or heat, and is unable to remember the shape of what initial container it is in. So it dissipates that heat or energy away. Now, solids, on the other hand, don't flow. They can only be deformed in this case. So in the case here of, like, say, a building or a steel structure, is if you apply a certain wind or stress onto it, it deforms and moves around in this case. So it does deform. So you can think of a slinky or a rubber band in this case. If you pull on it, it deforms, but it still holds its shape. And what happens, though, is because in solids have the ability to kind of remember their shape, their structure in this case. So it stores this energy. And as soon as you remove that force, it knows what it was beforehand. So it goes back to that natural shape in this case to maintain that combination behavior. Now, for the most part, though, most materials are not an ideally liquid material like oils, or an ideal solid like steel, stone, et cetera, in this case. They're kind of a combination of the two, which is what we call viscoelastic materials. They have a combination of both fluid-like responses and solid or elastic response behavior. So again, they may behave like a fluid, but they do have some ability to retain shape, even though they're dominating the case here, like a shampoo, which is a viscoelastic fluid, or a sealant, which is a viscoelastic solid in this case. And so rheology allows us to describe the material through any of these types of behaviored responses. And so again, taking that consideration of sort of why rheology is important is what is interesting is if we want to understand kind of the melting temperature. So where the sample transitions from being elastically dominated to liquid dominant from a temperature standpoint, we can look at the melt behavior, or also from the glass transition temperature, where basically the moduli become constant over a range of temperatures in this case. And so this is important from a processing standpoint because it helps us to understand kind of from processing where we can get the sample to start moving, or also from its final product behaviored responses. Likewise, if we're trying to understand, say, the ability for the sample to kind of recover or behave for fluid-like materials or viscoelastic fluids, we can look at the zero shear viscosity, which is looked at low shear rate behaviors, to see if we're going to have issues of the sample being able to flow or flow out, in this case, the sand point. Likewise, at high shear rates, is if the elastic behavior kind of has too much of an impact, this can influence, say, extrusion, injection molding, and even film blowing. And then likewise, if we have information from, say, the frequency sweep or the oscillatory measurements, which we'll talk about, is the crossover point of the storage and the loss modulus of functional frequency can help us give an idea about molecular weight or the molecular weight distribution of the material in that case. So again, it's a wide scoping thing that we use from a polymer processing standpoint. And so with rheology, how do we do these measurements? So from a viscosity or oscillatory standpoint, we control either the shear stress, the shear rate, or the shear strain being applied to the sample. So if I want to measure the viscosity, so we can look at Newton's law, which is simply the shear stress divided by the shear rate. And we have two modes in which we can do this measurement. So I can apply a certain force and see how fast the sample goes. So again, applying a force, seeing how fast it moves. Or in the opposite spectrum, I can apply a certain speed to the sample, or and measure how much force is required to stay at that speed, or additional speed in this case. So it's simply one or the other in this case. And then the same thing with measuring the modulus, which is simply the stress divided by the strain. So again, I can apply a stress and measure how far it displaced itself. So again, you can think of, say, a rubber band where you pull it with a certain force and see how far it displaces. Or the same thing also with like a weight band, is that you pull it a certain distance between your arms, and then you measure the resistance that you're seeing in this case. And so this is how we measure the responses. So it's fairly simple and straightforward in this case. And so what's of importance here in this case is if I'm measuring the viscosity of the modulus from a rheological standpoint, I control one parameter on the instrument and I measure the other back in this case. And then you should also be able to see is that it's not, viscosity is not dependent on if I'm doing it from a stress or a rate standpoint. I should get the same viscosity if I do it from a stress control versus a rate control standpoint. The same thing with the modulus. I can apply it in both standpoints in this case. And so likewise with rheological or viscosity or modular behavior, is there are different types of geometries that can be used. For low viscosity, low molecular weight fluids, I can use what's called a concentric cylinder. So again, for easily flowable material, so things on the order of, say, 100 to 1,000 centipoids or lower, that I can actually fill into this bob and ensure that I can get into there. However, commonly though, for most polymers, you either use a cone and plate. It's still used for very soft materials, flowable materials. Again, I have a small thin gap, which is somewhere between 50 to 100 microns, depending on the size of the truncation, which can be anywhere from 0.5 degrees for very low molecular weight materials, or very thin materials, to high pace materials, which is about six degrees in this case. Now, we have to be considerate though, if you have large particles, you don't want to have them underneath the gap, because again, they can kind of agglomerate together and create a superstructure which creates that response. Or for very stiff materials, we have a parallel plate. So again, it can be used for ideally free-flowing materials, elastomers, very rigid materials that cannot get down to very small gaps because of the high molecular weight and the normal force that's applied to those samples. And so as these are all kind of considered absolute geometries, if I'm dealing with the same kind of sample and these all meet those specifications, it will give me the same response in that case. But what you should see from this is we have a well-defined shape due to the small gaps and the known behaviored responses in this case. Now, getting into what is viscosity. So again, viscosity is just the tendency to kind of, resist flow under applied forces. So depending on what the temperature is, it's highly temperature dependent, as you can see from the image, is on the right is it's very easily flowable, or the blue ink, because it flows out very easily, whereas the yellow oil in this case has a higher viscosity because it holds itself together better. Now, as I increase temperature, I can change the viscosity because viscosity will kind of decrease as a function of increasing temperature. And so in the case of materials, if there is no structure into them, we can kind of talk about viscosity as a single point response. But in most cases, materials have some degree of structure. So you have to look at them as a function of, say, a curve, because different shear rate conditions impact the behavior of the viscosity, and the viscosity just changes as a function of both temperature and the shear history you apply to it. And so the reason why viscosity is important, as I said, is because if you're dealing with something that has structure, depending on what your conditions are. So for instance, if I'm interested in looking at sedimentation or how stable the material is, I focus more at low shear rate conditions. So thinking of sedimentation, leveling impacts. Those are at very low shear rate conditions. But if I'm actually looking at, say, extrusion or stirring, these are at extremely high shear rate conditions. And so the only reason why your viscosity would be the same is if the sample was, say, in essence, Newtonian. But in the case of most structured materials, as I said before, the viscosity does change. You may have a decreasing viscosity. And so the behaviored response changes. So you have to kind of accommodate for those particular needs and consideration. And so there is a shear rate for every type of application out there. And so from a flow standpoint, most materials will fall into one of the four categories here. So you have what's called an ideally viscous material. So again, Newtonian in nature. So the viscosity doesn't change as a function of shear rate. It's constant overall. It's only impacted by the temperature, or if you're talking about it from, say, a drilling aspect in this case, the pressures as you apply higher and higher pressures, those impact the response of the behavior. Now, most materials, though, of interest are kind of what we call shear thinning. So they can either be called a viscoelastic liquid or a pseudoplastic. In essence, what we see for those materials is at very, very low shear rates, they have this plateau, which looks very much like an ideally viscous material. So they call this kind of a Newtonian plateau. As I overcome this behavior, or this Newtonian characteristic of what we call a zero shear plateau, is the sample starts to show this shear thinning behavior because the elastic behavior starts to align with the flow field. And so at higher and higher shear rates, the viscosity decreases further and further. Whereas in the case of viscoelastic gels, so these are things like thermosets, is at rest conditions, the material behaves like a solid. So it holds its shape, it holds its structure. So things like ketchup, hydrogels, paste, they all hold their shape and condition at very low shear rates. But as I start to apply any shear conditioning to it, the system actually starts to shear thin, which is why we see a shear thinning response or a decrease in the overall viscosity. Now, on the extremes of this is what we have are called shear thickening or dilating responses. And so you can see from the video here, we call this a viscoelastic paste. And so what these materials happen is you have a high solid content, somewhere on the order of, say, 20 to 40% of solids in a solution, or some kind of oil matrix or fluid matrix, is these hard particles basically at very low shear rates can easily pass each other. So it behaves like a liquid, as you can see with the person who's sitting kind of in the fluid, who's kind of just floating around. Whereas at high shear rates, it allows that these particles can't pass each other. So you have this jamming response, and then the material basically hardens up. or becomes thicker in this case, which holds those conditions, as you can see by them being able to run across the system. And so these are kind of unnecessary things you don't really want from, say, a processing standpoint, that you have shear thickening, because you don't anticipate a material becoming thicker or more resistant at higher and higher shear rates in this case. And so in the case of what causes the shear thinning response, so as I said, it comes to the fact is that you have particles or molecular orientation. So again, you have structure that's oriented with the alignment of the flow field. And this can happen in polymer melts, suspensions, emulsions, and even dispersions. And so what happens in these materials is at very, very low shear rates, you have this high viscosity, because you have, in the case of polymer melts, you have these entanglements that are kind of encoiled, and they're in this, undisturbed state. So they have this high viscosity because they're entangled. There's a lot of entropy in this case because they're relaxed from that standpoint. Now, as I start to shear the sample, I'm taking these long chains and pulling them apart and aligning them. So I'm creating some degree of order in that case. So from that applied shear, I take it from a disorder to a very ordered type state, which is, you can say in the case of, say, dispersions, they're randomly uncoiled around, and eventually they start to align with the field conditions, as we can kind of see from the imaging. Now, in the case of viscoelastic fluids, though, we have this zero shear plateau. And so it's different than, say, a viscoelastic paste or a viscoelastic solid, which shows a continually increasing viscosity as we decrease the shear rate. And that's because in these unlinked polymers, you have two competing processes. You have the fact is that you're orienting the sample because you're applying flow, which creates the viscosity decrease. However, as there's an elastic component, this wants to recoil. So it wants to re-entangle and align, which creates a viscosity increase. And so now you have kind of these two competing processes. And as the viscosity is not able to change, you have this zero shear plateau. So you're continuing to increase shear, but the fact of orientation isn't high enough to overcome the elastic contribution. It's not until you get to higher and higher shear rates that you see this viscosity decrease, as you can kind of see in section 2 of the graph. However, eventually, though, you get to a certain shear rate where you have this secondary plateau where the sample is fully aligned with the flow field. So we know this as the infinite shear viscosity. And so from this, we can kind of get some information from modeling as to what the zero shear viscosity is. And so in the case of this, the zero shear viscosity is important because from that, we can garner that information out from various models, the Crow model, the Crow-Yasuda, the Cross model. And the reason why it's important is from the zero shear viscosity, it gives us an idea about, say, the concentration of the material, or also if we're comparing materials of the same nature, do we have some similar molecular weight or higher molecular weight, as you can see. So as the zero shear viscosity shifts up or down, it's an indication about the molecular weight change or concentration changes. Likewise, the range or shear rates at which the zero shear viscosity is. So at lower and lower, if the lower shear rates, it moves from, say, the zero shear plateau into what we call the power law parameter for looking at the shear thinning response. This tells us some information about the molecular weight distribution. So the wider it is, the narrower the distribution, the smaller it is, the broader the distribution in this case is. So again, this gives us quite a bit of information about the processing conditions, about how easily does it shear as we go to higher and higher shear rate conditions. Likewise, the viscosity behavior is influenced by, the filler in your material. So if it's just simply a polymer without any filler into it, we see a viscoelastic fluid. So the viscoelastic behavior, we see the Newtonian plateau followed by shear thinning. As I add some concentration, so again, putting filler into there, so it's not creating any kind of conditions. At higher shear rates, the behavior still shows the orientation of the structure, which is fairly similar. It's just I have a higher viscosity at lower and lower shear rates. Eventually, though, if I have a high concentration of the filler, again, I get a much higher viscosity, so it's much more, requires more pumping to get it to start flowing. And if I have too much concentration, you can kind of start to see that the plateau, or at higher shear rates, the viscosity starts to look like it would start to trend upward in this case. So showing more of a dilate and response behavior. So again, these are all things to kind of look at in terms of the interactive forces in your material. Now, that's all looking from a rotational standpoint in this case. So, however, though, this just gives me about viscosity for processing standpoints. If I want to understand more about the behavior, I look at it from an oscillatory standpoint, which kind of gives me an idea about how to kind of break out what we call the viscoelastic contributions. And so the way this is done is it's simply put is we wiggle the sample back and forth. So you can think of, say, Jello, you're just wiggling it back and forth. And it's this nice sinusoidal response under different frequencies or different stress or strain amplitudes. And the beauty of these types of tests is that they're considered non-destructive in nature because, again, I stay within what we call the linear viscoelastic region. So it doesn't affect the material, which we don't see from a rotational standpoint. As soon as you shear it, you break the material down and change the behavior in this case. So you have to start with a brand new sample. And so from this, we introduced a series of parameters. We have the stiffness, which we call the shear modulus or complex shear modulus, which is G star. And that comes from the stress and the strain response from the sinusoidal behavior. And then from that, we can kind of break down using kind of, vector math in this case, where the stiffness is the modulus. We know the phase angle from how far apart the moduli, the stress and the strain moduli are from each other. And this gives us what we call as our storage modulus, which is the elasticity of the sample, and the viscous modulus or loss modulus, which gives us the viscous contribution. And depending on the phase angle, this tells us how liquid or how solid it is. So now I have the ability to say exactly how elastic and how viscous it is, which is I couldn't say from a rotational standpoint or flow curve standpoint. I could just say I have some elasticity because that's what's causing the shear thinning to occur. And so in the case of these oscillatory measurements, so if the loss modulus, which is G double prime, is greater than G prime by like 3 to 4 orders of magnitude, we consider that a purely liquid response. So ideally, tan delta goes to infinity. Whereas we build structure, tan delta goes more towards 1. And then when the moduli are equal to each other, this creates a gel point where you have equal tendency between the viscous and the elastic response. And then as tan delta goes towards 0, it's more elastic or more structured in this case. And so we can now get an idea about the balanced behavior of that system from there. And so the reason why oscillatory responses are behavior, because again, it gives us an ability to understand what's occurring in the elastic contributions, which is something we don't see from a rotational standpoint. So you can have things like die swelling. So die swelling comes from the fact that you have too much elasticity. So too much memory, it didn't have enough time to relax and remember its shape, or melt fracturing, which comes from too much elasticity at higher processing speeds, as well as starch shearing. And so from that, we can look at the oscillatory measurements to kind of give us an idea about how to modify that, either by putting, say, additives to adjust down the elasticity, adjust the modifications of likely distribution to shift that to lower or higher frequencies. And then also if we're looking at, from a processing standpoint, the Deborah number. And so you want to try to make that as low as possible to have the best process from a processing standpoint in this case. And so one of the major measurements that is done from an oscillatory standpoint is what's called a frequency sweep standpoint. So in the case here of how it's depicted is I increase the frequency. So I shake the sample back and forth at either increasing or decreasing frequencies at a set strain or set stress. And depending on how the material responds, I see the storage and the loss modulus change as a function of frequency. And from that, you can kind of fingerprint the material. So short-term relaxations relate to, say, high frequencies. So, extrusion behavior response would be high frequencies, whereas at stability or response behavior, that's long-term relaxations or low frequencies in terms of that. And so depending on the behavior, if we see a crossover point, there's an indication that we have a zero shear viscosity plateau, which can relate back to molecular weight distributions or molecular weights. Or if we don't see a crossover, it may indicate something about cross-linking stability or impact resistance. And so just from that, like I said, is we can use the frequency sweep curve to kind of use it as a fingerprinting response. So if I have a thermoplastic, and we just look at the storage modulus, is you will see it has a much more broader decrease in the overall viscosity, or sorry, not the viscosity, but the modulus, because again, the crossover point is going to be at a much higher frequency. So it's a narrower molecular weight distribution without really any cross-linking in that case, which is seen in image 1. Whereas if it's a much broader distribution, the curvature shifts to decreasing, say, to lower frequencies. Whereas if the sample does have some degree of cross-linking, is we'd see that the modulus doesn't kind of, it eventually softens, in this case it goes down, but we eventually see a plateau as shown because there is some degree of cross-linking, so it doesn't have the ability to relax. Whereas if it's completely cross-linked, its elastic behavior is not frequency dependent in this case because it has a high structural integrity at rest in this case. There is no response behavior. So it has basically this, you know, slope of 0, whereas say 1 and 2 start to show to a slope of 2 from say the Maxwell model behavior. And so if we look at that from an amorphous standpoint, as I said, at high frequencies, the sample behaves like a solid. So you can think of this as say PDMS. So if you think of PDMS as you grip it real quickly and pull on it real fast, it behaves like a solid and snaps. Whereas if you pull it very slowly, which is low frequencies, it behaves like a fluid and will start to kind of relax and level out in this case. And that's also further shown in the green portion of the curve, which is the complex viscosity. And we see a plateau or zero shear plateau, which we list here as 35 kilopascal seconds. And that's kind of expected because when we see a crossover, this is an indication of a viscoelastic fluid or an uncross-linked, say, polymer melt in that case. So it's going to have instability because, again, the viscous contribution dominates at rest condition. And so to kind of go back to the frequency sweep in this case, at the crossover point, this kind of gives us information about molecular weight distribution and molecular weight. So as the frequencies for this crossover point shifts to, say, higher frequencies, this is an indication of a low molecular weight material because, again, you have smaller chains. Smaller chains relax much faster, whereas longer branched polymers or molecules take longer to kind of relax, which is why that crossover point would shift to lower frequencies in this case. Now, as that crossover point shifts up and down on the y-axis, the lower it is, the broader the distribution, whereas the higher it is overall, the narrower the distribution. And this is actually seen here, where we look at 3 different polyethylene melts. So in the case of linear low density polyethylene, LLDPE, the crossover point is shifted to the highest frequency because it has the smallest chains. And also since they're very much the same chain length, that crossover point on the Y scale is shifted to the highest point, whereas something like low density polyethylene or LDPE is somewhere in the middle. So it has, you know, a moderate molecular weight, but also it has a broader molecular weight distribution overall in this case. And then high density polyethylene has the highest molecular weight since the shift is to the lowest frequencies, and then just slightly, you know, not as broad in terms of compared to low density polyethylene. So this is a way to actually compare the materials back and forth from that standpoint. Now, likewise, if you're comparing materials, if the sample does have structural cross-linking into it, you can see in the case here of a polyethylene with different functional groups, is in a cross-linked and uncross-linked material, they behave very similar. They have roughly the same elastic contributions and the viscous contributions. The differences show up, though, at the lower frequencies where we see that the cross-linked polyethylene starts to have, say, a plateau in the storage modulus at lower and lower frequencies, whereas we don't see that. We see a crossover point, so we have instabilities due to the fact of there being no cross-linking agents in the blue data, which is the uncross-linked polyethylene. So again, seeing differences can give us a gauge of the material response. Now, in the case of frequency sweep data, is we're limited on a rheometer to about 100 hertz or 628 radians per second, depending on how you see that. And so to get to higher and higher shear conditions, or to replicate to that, we can use what's called time temperature superposition. Is because what we know is that as you increase or decrease temperature, the relaxation times get shorter with increasing temperature, and they get longer with decreasing temperature. And so by using shift factors, we can do very short frequency sweeps and shift the data along the x-axis to give us kind of a reference condition to kind of increase the response behavior. And this allows us in a very short period of time to understand what's going on with the elasticity response. And so if we look at that, just looking at the storage modulus, what you should see in the data is, again, you first pick a reference temperature, typically in this case for 200, is you should see the shape of the curves for all the different temperatures look fairly similar. It looks like you can shift the data fairly easily in this case. And so lower temperatures shift to higher frequencies, whereas higher temperatures shift to lower frequencies. And so now this allows us the ability to kind of expand the data path out in a very short period of time. And then from that, it gives us a better understanding. So in the yellow is roughly what a rheometer can do. And by using time temperature superposition theory, this allows us to shift the modulus to get a better understanding in this case. Now, certain things you have to do with the data is to kind of prove through what's called the Cox-Mears rule, is you would look at your frequency sweep data, compare it to rotational data, and if the complex viscosity and the rotational data overlay to each other, this indicates that your data and your material response behavior, that this should technically hold in that case. And there are ways of looking at it that you should see a fairly easily shifting behavior. But again, it's not doesn't hold for every material, so you have to look at it on a case-by-case basis. Now, what we can also do is, outside of just looking at these from a isothermal response, is we can look at the material behavior as a function of different temperatures. And so the reason why that's important is because if you're processing the material, or if the sample has to go through different temperature conditions, it just gives us an idea about, if you're doing something where you may have a reaction kinetics or thermal stability, as well as from a processing window standpoint. So this helps us to determine things such as gelation and curing, if you have melting or glass transitions, as well as kind of understanding about the kinetics of the system. And so typically the materials or polymers will fall into kind of either amorphous. So again, we see at very low temperatures, the storage modulus dominates. Again, as we go to higher and higher temperatures, the sample begins to become, unordered in this case. So it goes from a solid to a liquid, so it becomes more flowable in this case. Whereas in partially crystalline materials, where you have some structural behavior, you'll see it behave like a solid in the glass transition temperature. We see this kind of plateau or rubbery elastic plateau region, followed by, at higher temperatures, that the sample goes through what we call a melt temperature, where the sample transitions from a liquid or a solid to a liquid with increasing temperature in this case. Whereas if you have, in essence, a thermal set or an elastomer, where you have these chemically cross-linked materials or bonded material, again, it has a glass transition temperature where it becomes a very rigid material, and then it softens, but we don't see the moduli ever cross in this case, because again, those cross-linking agents keep it from interlocking or being able to flow or relax in this case. And so you have these different behavior responses depending on the material. And so in the case here, if we look at, say, a hot melt adhesive, again, we see it, cold temperatures. We see the glass transition temperature where the storage modulus starts to drop down. You can also look at it from tan delta, where we see a peak in the tan delta response, which is typically how people look at it. We then see the sample soften. We see the secondary plateau regime, which is kind of the region in which the usefulness of that material, or what we call the rubber elastic regime, followed by, at higher and higher temperatures, that the material begins to melt and becomes more disordered in this case, because again, it's behaving more and more like a fluid. And so this kind of gives us an idea about, okay, if I need to process it as a fluid, I need to have a melt, I need to process above 80 degrees, because again, now it's behaving like a fluid at higher and higher temperatures in this case. Whereas in the case of rubber or elastomers in this case, again, we still see the glass transition temperature, so the storage and loss modulus are constant. We then start to see the material soften, so we go through the glass transition temperature. But unlike what we saw in the hot melt adhesive, we don't see the response behavior of the viscosity or the storage and loss modulus kind of shift to each other in this case. So we don't see any tendencies for those storage and loss modules to go because of that cross-linking, which keeps it from behaving like a fluid at higher and higher temperatures. It behaves like a solid throughout this. It's a softer solid. Now, additionally, we can also do things where we kind of track the material response. So instead of just looking at the material behavior, if you have kind of reaction kinetics, is you can talk about a epoxy powder coating. So you have a melting behavior. So again, the glass raises temperature, it melts, it's softening. As we get to higher and higher temperatures, we eventually see that the modulus plateaus. And then it's at this point that we're at a critical response behavior. So roughly at a temperature of about 260 degrees, which is seen by the green triangle, is once we overcome that temperature, the material starts to kind of cure, which is now seen as in the blue portion where the viscosity or the moduli kind of continue to increase as a function of increasing temperature. Now, as I apply more heat or more energy, the curing response gets faster and faster and faster until eventually with the black, I see what we call a salt gel transition, where the sample transitions from a liquid to a solid. So it's kind of the opposite of melting, except we're now talking from a curing standpoint because the cross-linkers are triggered by that increased temperature. And then as I go to higher and higher temperatures, eventually the reaction stops or slows down because everything is fully cured. And I see a plateau in both the storage and the loss modules where the sample is a fully cured kind of conditional behavior. And so I can look at that from a temperature standpoint to see where the onset of curing behaviors occurs. Now, this is just from a temperature curing standpoint where I continue to increase temperature, the reaction gets faster and faster, but I can also look at the behavior under isothermal conditions of looking at temperature at different temperatures. And so again, looking here at this powder epoxy coating. So I'm loading the sample at these different temperatures. It gives me a window in terms of the processing. So at lower temperatures, the reaction is slowed down, as you can see in the black curve, where the crossover point occurs roughly at about just under 1500 seconds, whereas if I increase the temperature by 20 degrees, it occurs in less than 10 minutes. And if I even go 20 degrees higher at 160, I see that the crossover point is roughly within 100 seconds or so. And so this gives me an understanding is that if I change temperature, my processing window for where the sample becomes flowable to non-flowable is greatly changed in this case from that standpoint. Now, what I kind of talked about there is kind of from a basics from, say, a shear or shear oscillatory standpoint. Now, there are other things, like for instance, if you're talking about blown film, or you may want to look at it from an extensional standpoint. So you can either do that with, an extensional system, such as what we call the Setmanot extensional rheometer, or the SER, or a universal extensional fixture, where you apply a rotation and pull the sample in a uniaxial direction to kind of understand the behavior from an extensional standpoint. And this can be done under both rotation or oscillation, or what we call kind of, we're looking at kind of solids, which is how we look at tensile behavior. And so tensile behavior comes from Young's modulus. So we have E, we have a tensile stress sigma, epsilon is the strain or displacement that we put behind that, and there is a ratio between, say, the shear and the tensile modulus, which is known as Poisson's ratio. Typically, the Young's modulus is 3 times that of the shear modulus, but if you do both of the measurements of your material from both a shear and a tensile response, you can get Poisson's ratio out of the data. And so one of the common techniques is what's called a transient extensional measurement. So again, you apply a set shear or tensile rate, and you see how the material behaves as a function of that. So you can see things such as strain hardening or melt fraction, which aren't easily able to be obtained from, say, a shear standpoint in this case. And so if we look at that in the case here of a linear polymer, so the open square data is from a viscosity standpoint. So we use what's called Troughton's ratio. So we multiply the transient viscosity data by 3, and it gives us this curve. And so what we see in this case of this polymer melt is that as we increase the extensional rate, so going from 0.5 to 1 to 10, the sample breaks at a much quicker time, which is why we see kind of the breakdown of the system. But we don't see any kind of of response. We don't see any increase in the behaviors that would kind of tell us something about strain hardening. So instead, we consider these kind of what are called strain softening response behaviors. However, in low density polyethylene, or LDPE, we see a completely different response. We see that as we kind of go to longer and longer times at these set held shear rates, we see this increase in the extensional viscosity. This is because as we pull it in the extensional direction, the sample starts to align with the flow field, and we have this what we call strain hardening. You can then quantify kind of if there's some cross-linking based on the ratio between what the viscosity should be at on the linear range curve, or from Trotman's ratio for steady state, to what the peak point is in the extensional response behavior. And so again, this gives us an idea about how to look at strain hardening, which is something that you can't do with a purely rotational standpoint. So again, looking at different ways from that standpoint. Now, likewise, if you look at from a tensile standpoint, so if you're dealing with solids, you can't really do anything from a shear standpoint. So I can't put in a cup or bob, parallel plate, or Conan plate because of how stiff the system is. So again, putting it in an extensional device, I can now measure the glass transition temperatures. And if I'm dealing with different materials, I can look at, say, if I'm dealing with, say, a blended material, I can see in this case if they're miscible in each other, which is what we see here in the polymethyl methacrylate or polycarbonate, which don't mix with each other. I see two distinct glass transition temperature points. Whereas if they are miscible in each other, you would have kind of a single point, and it would shift one way or the other depending on what is of a higher precedent for your material. And so with that, hopefully what I've given you from this is you can see that rheology provides kind of a means to characterize viscoelastic behaviors, to understand polymers, not just from a fluid standpoint, but also to understand its elasticity, whether it be a thermoplastic or a thermal set or a thermal resin, as well as kind of using these various different types of techniques that you can employ to kind of fingerprint your material under different conditional responses. And then likewise, is with the rheometer, it's not simply just doing these oscillatory techniques. You can apply different things to do things such as tack, tribology, to look at friction behavior. You could look at kind of the response behavior from a microscope, which I didn't talk about, to get kind of that understanding about those conditional behaviors. And so with that, I'll open the floor to any questions you may have.
Thank you. Let's take some questions from the chat window. First question, what is the difference between shear rate and frequency?
So what shear rate is from a rotational standpoint, is basically how much the speed at which you're applying it to move forward in one direction. So you just move in one direction overall in this case. Whereas frequency is, you can think of it in two ways. So most people consider it either frequency, which is denoted as F. Usually that's how fast you wiggle it back and forth. So again, you have, say, something like 1 hertz or 10 hertz. So that's how often a cycle occurs. So again, if you think of wiggling Jello back and forth, from moving one way and back, how fast does that occur? So that's roughly, if you think of a frequency of 1 hertz, that indicates that you wiggle the sample back in a sinusoidal fashion in a 360-degree pattern in 1 second. 10 hertz, 0.1 second. There's also what's called angular frequency, denoted as omega. And so it's the relationship between frequency F and angular frequency is 2 pi F. So this is why I said so if you talk about 100 hertz, that's an angular frequency of 628 radians per second.
Next question, would TG always be less than TM?
Yes, traditionally the glass transition temperature happens lower than the melt, because again, if you have something that does melt, it's behaving like a fluid, and then it does start to kind of, you have that crossover point followed by the plateau in the storage and loss modules. Now, if you're dealing with, say, for instance, the best example I can give is what's called water. So in those cases, those materials crystallize very quickly. So you have, in essence, you have your crossover point, and then within a second or so, the material basically has set up and hardened. So that's not a melt, and a transition, it's what we call a crystallization point. So there's some differences from that standpoint in that case.
Next question, can you measure shear rate and strain at the same time to get viscosity and modulus from the same experiment?
So depending on the nature of the material, so as I said, if you apply shear rate to a material, or if you're applying that, it's considered what we call a destructive test. So if you break the material down, I mean, you could then apply a strain, like from an oscillatory standpoint, and look at the behavior. But if the sample hasn't recovered, you're not comparing the sample under the same conditions or rest conditions. So you can do things from, say, what we call this thixometry, where you look at, say, the recovery behavior. And if you allow enough time for the sample of recovery, then you can actually correlate that response behavior back. So you could actually do the test. You can program it to do a shear rate control, and then it followed by a strain control in this case.
Next question, rheological properties measured in a semi-solid state of material be correlated to the solid state properties measured by a universal testing machine. For instance, a solvent gel that can be converted to a fully solid porous foam or something similar.
So, I mean, so you could do some compressional measurements, and then from that, I mean, you would have, say, the force and the gap change, which you could then correlate that back to some degree of stiffness. So you could use the rotational rheometer to do it in that standpoint, yes, to understand, say, the stiffness of the material.
Next question, in thixotropes, shear thinning materials, does hydrogen bonding play a role?
So, I mean, the bonding does play a role because it's going to create some kind of structure to it. So depending on how high of a bonding it is, it does have an impact because it's going to create something in terms of various stiffnesses. And then again, with the thixotropic material, there is going to be some degree of recovery. So how those bonds either recover, or if you broke them down, that's going to change the behavior response in that case.
Next question, how to relate G prime or G double prime to dye swell, shark skin, etc., in common processing issues?
So in the case of processing conditions, because like I said, those occur at very high shear rates or high frequencies. So if you have these impacts, if you have dye swell, so dye swell is the ability to kind of remember its shape. So you take it from a very large container to a small container, and you don't allow enough time for the sample to relax. So it's still remembering that. So the higher the elastic contribution overall at those high frequencies, the more likely you're going to have these things such as dye swell or shark skinning. So the way to kind of reduce those is you would use some type of modifier, or you would make the sample, in essence, what I would call, say, softer, by lowering the elasticity. So the lower you can make the elasticity, the less likely these instabilities in terms of dye swell occur in that case.
Okay. How many measurements do we need for one experiment curve in general?
So, I mean, so in terms of processing, so if you're doing it, say, to kind of get, to understand the material, typically in general, you would do 3 measurements of the same material to get kind of a baseline, because then you could average over to see what your variation is from measurement for that particular sample, to see if there's any variance from that. But in general, if you're talking about, how long in the measurement, then you would just adjust the parameters to ensure what you have is kind of steady state for those conditions.
Okay. Just wanted to make sure if the curing behavior under thermal conditions vary when applying different shear tensile strength conditions.
Right. So yeah, so that is a good question. So if your sample does go through a curing process, or even if it is softening in this case, there is what's called the linear viscoelastic region. So in the linear viscoelastic region, this is where where the sample undergoes, no destruction. So it's basically able to always recover back. We're not putting any permanent destruction in the response behavior. And so in the case of, say, if you're doing this a temperature sweep or temperature ramp. As the sample softens, if you keep the strain the same, the torque or the stress decreases, so you get into limitation of the instrument. So you can either increase the strain to stay within the linear range still. You confirm that by doing a high temperature and low temperature. Or in the case here of the question, which is from looking at a curing standpoint, your sample is getting from a liquid or a very soft gel to a very stiff gel. And so what you would do is you would look at what we call the linear range in the unconditioned sample, so its base behavior, and then look at the condition in the final standpoint. And if the strain change, or if the linear range changes, you would want to adapt your test to adjust the strain so it's always in the linear range. Because once you move outside the linear range, your sample is no longer at true rest conditions. You're breaking the material down unnecessarily.
Okay, next question. What will be the response of curing thermoset resin under loaded condition?
So in the world of rheology, you usually want the sample to be relaxed. So what that means is you want to have a normal force or normal stress conditions of 0. So the sample should be fully relaxed. And so if you apply a certain force to the sample, so you're putting pressure onto it, which is very much the same thing if you're doing, say, drilling under the earth. As you apply more and more pressure, the viscosity increases. So your response of your material, if you're comparing it, from applying, say, if you're keeping a force of 1 Newton versus, say, 10 Newtons, as you increase that pressure, the force, or the response behavior is going to increase as a function of that applied pressure.
Next question. For rubber temperature sweeps, if we rise the temperature all the way up to 300 Celsius, is it normal to see a drop first, a plateau, and then a drop again? I wonder what the reason for the second drop is.
So, all right. So at the higher temperature is if you're seeing, in essence, a decrease in the moduli. That could either be because the sample is softening. It depends on the material. If it's a thermoplastic, and depending on what conditions you're using, usually these are tested under inert conditions. You might have thermal degradation, so that's what's causing the material response to decrease down. I mean, ways of checking that is you can do, say, GPC analysis to look at what the material molecular weight was before versus what it is after all these conditional responses.
Next question. For plastics, we used MI to predict plastic melt property, but measuring MI doesn't use shear rate. So what's the difference between MI and actual melt property?
So in the case of MI, or which is called like the melt flow index, it's a simple technique in terms of looking at like a quality control. So it looks mainly at really low shear rate conditions, and it can be a useful tool. But in the case of, say, rheology, is we look at both low shear rate and high shear rate. And so if the conditions of what you need from a processing standpoint is you may have similar materials that have the same melt index or melt flow index, but they process completely different. That's because at the higher shear rate, which is what the melt flow indexer isn't looking at, is they look completely different. So this is usually why in the case of what we call non-Newtonian or plastics or polymers for the talk, is why we don't look at single point measurements. So anytime you have structure, you look at it, like I said before, as a curved response in this case, and then try to focus at the shear rate that's of precedent, because you may have a sample that have the same melt flow indexes, but at really high shear rates is where you're processing, they look completely different.
Okay. What kind of behavior can you see from gels in LLDPE versus HDPE?
So in the case of gels, so what you would see is in the frequency sweep is you would usually see the storage modulus always dominates because it's a gel. So there's some structured behavior there that's keeping it from resting. That's why it holds its stability. I mean, examples of that you can think of, say, ketchup, toothpaste, rubber. They all behave like a solid at rest. They don't relax. They hold their structure. Whereas for things like LDPE and HDPE, if you get them high enough in temperature, they do start to melt in this case. And so at high temperatures, high frequencies, they behave like solids. And then as you go to lower and lower frequencies, they behave like fluids. Now, depending on say the molecular weight or the chain lengths, you'll see shifts at the crossover point. So, you'll see differences from one material to the other. So it depends on kind of the molecular weight of HDPE and LDP as to how they behave, as well as the distribution in that case. So you look at the frequency sweep to kind of get a better understanding of comparison.
At one point when you were discussing frequency sweeps, you mentioned that measurements can sometimes highlight impact resistance properties. Could you expand on that?
Right. So what that would relate to is, so in the case of, say, elastomer, so high frequency. So again, if you're looking at it from a dampening standpoint, so the higher the moduli at those cases, it's going to help dampen out. Sorry, not dampen out. You would look at kind of what's called tan delta. And so depending on how tan delta is, you either have it very close to 1 or just slightly below 1, because it's still behaving like a gel. So it helps to dampen out the response, because if it's too stiff, it behaves like a brittle solid in this case. So depending on the nature in this case, you want the storage modules to be more dominant. And depending on that, you can look at that. So like, for instance, in applications for aerospace resins, they design it so that it can dampen out based on the moduli at those higher frequencies for that reason.
Okay, next question. Do you have some application for engine oils or similar fluids?
So I do. So I mean, there are some applications we have on various engine oils, either from, say, just looking at the viscosity, or also if you're talking about it, say, from under pressured conditions for like drilling applications, as well as from a tribological standpoint for, say, frictional behavior. So yes, we do. So if you want, you can email me from the slides, and then I can send you the necessary information.
Okay. If we want to generate the TTS plots using a range of temperatures, should we perform a strain sweep at each temperature to determine the critical strain for the linear viscoelastic region and ensure that the strain used in the frequency sweep falls within the LVR at all those temperatures?
Yes. So one of the tests I didn't talk about, just because of time, is what's called an amplitude sweep. So this is where you find the linear viscoelastic region. And so normally what you would do in the case of time temperature superposition is, depending on what temperatures you're going to be testing, you would start at the lowest temperature and do an amplitude sweep and find the linear range, and then also at the highest temperature to also measure the linear range. And so that way, then you could adjust the strain at those different frequencies to stay within the linear range, so that you don't go outside of it, as well as you go to higher and higher temperatures, that the sample becomes softer and softer, that you stay within the limitations of the instrument as well. Yes.
Next question. I'm trying to understand the difference between response time and time of observation used in the Deborah number. In the context of a frequency sweep, is the time of observation simply the inverse of frequency? And how does this relate to the material's response time?
So in the case of, say, the frequency sweep, so you have your response time, which is your lambda, or your relaxation time. So that's normally, from a frequency standpoint, the critical relaxation time is kind of considered the crossover point. So when the crossover point occurs, that's your the inverse of that frequency is your relaxation time. And so depending on that, and then you apply, say, your rotational shear rates, that would give you kind of an indication about the Deborah number from there. So it has to do with the material behavior response.
Next question. If the linear viscoelasticity region is very small, for example, 0.05% for a suspension, can we still use this amplitude for a frequency sweep, or such a small amplitude is just not useful?
So you can. There are things you would have to do. So if you have a very limited linear range, is you can still do your frequency sweep. You'd have to stay within the linear range. However, to ensure that you get a good signal of the system, you may have to increase the surface area. So in the case, depending on what the viscosity is, you may have to use a larger plate, or go to a cup and bob or double gap system, depending on how low in viscosity is. And so there are ways to that, even though if you have a really limited range, you can still do those tests. It's just you have to make sure you stay within or ways in which you can use different geometries to stay within the limitations of the instrument to get a good signal.
Okay, next question. What is the rheological behavior of LCPs when it is subjected to shear rate? Also, they often show lower viscosity at higher shear rate despite high molecular weight.
So, I mean, in the case of those materials is that, I mean, so even though if a material has a high molecular weight, I mean, there's some degree of elasticity into it. And so you will see that as you go to higher and higher shear rates, the viscosity tends to decrease because you have an alignment of those liquid crystals, liquid crystal polymers, because they're aligning with the flow field. And so the alignment or ordering of that structure is what creates this decrease in viscosity, which is why you see this shear thinning response.